Very well. Welcome to the second video in our video lecture series on R programming. In our first lecture in the video lecture series, we talked first about installing R, then how to install RStudio, and then I gave you a brief walkthrough into RStudio, as well as opening our first R project. So if you need help on any of those topics, refer back to the first video lecture. If not, in this second video lecture, I'd like to cover a couple of programming basics. We'll start first with commenting code. We'll talk then about some data types that are important to understand. And then we'll get into some very important data structures for R, such as the vector, the matrix, and the data frame. Let's go ahead and get right into it then. If you followed the first video lecture, you should already have an R project going. Make sure to open up RStudio and jump into the R project that we originally started with you. If you need to start a new one, go ahead and start a new project and just follow the project creation wizard. If not, just go ahead and select the project from the drop-down menu here. Once you're in your R project, you should see it in this files under the directory that you're in. And go ahead and let's start a new file and R script. This is stuff that we want to save for future use, so let's go ahead and file, save as, and give it the title R scripting basics.r. And we'll save that. You can see that the name has changed up here now. So the first thing I'd like to talk about is commenting code. I can't tell you how many hours that I have personally lost because of poorly commented code. Be that my own fault that I didn't comment my own code, or somebody else's fault that they didn't really provide clear instructions or clear explanation as to what they were doing with their code. A comment in code is essentially just a portion of text that's there not for the computer to interpret, but for us to understand what the script is doing. We add these comments by first adding a pound sign or a shebang, and then we can add whatever text we want to the right side of the pound sign. Anything on this same line to the left of the pound sign will be seen and interpreted by the computer as our code. Anything to the right of the pound sign will be ignored and is there for our convenience. You'll probably see me throughout this lecture series use a double pound sign. That's just kind of a stylistic thing that I started using when I first started programming, and you'll probably see me use that habit from now on. Now, thinking about this script, a couple of important things that we might want to communicate to anyone who looks at this script is, first of all, our name. So I always include my name at the top of any script that I write. I'll also give the date, just for context for my own reason, and believe it or not, it is 2022. And then I'll also give my personal email. I give my email address at the top of my R scripts because if somebody ends up with this script and has a question about it, or wants to collaborate on a project together, or for whatever reason they need to communicate with me, they have an easy way of doing that with my personal email, and they just send me an email. The last thing that is probably important to put as a comment at the very top of our script is a little explanation as to what we're trying to do with this script, or what our main goal is. For us right now, our main goal is just to run through some basics. So let's just leave a comment just running through some basics. Now let's give an example of commenting a specific line of code. I promise this is the last time I'll give you guys this example, but in our first lecture we talked a lot about the hello world of our programming being making a histogram with a normal distribution. That's just kind of a joke at this point, but for anybody who is new to R, looking at this R norm 200 might be pretty confused, and that might be you at this time too, kind of confused as to what's going on. At any point where you think either you will forget about what this line is doing, or you think that your user might not understand what's going on in that line, you probably want to add a comment just explaining what you're doing with it. So rnorm is a function that just randomly selects parts of a normal distribution from negative, with the mean centered around 0 actually, and then returns those random numbers. So returns 200 random numbers in a normal distribution with the mean equal to 0. And that's just an example of using a comment after a line of code. Remember, anything to the left of the hashtag or the shebang is seen by the computer and ran by the computer, whereas anything to the right is entirely ignored and is there for our own understanding. Just as an example, the computer ran this specifically, even when I ran the whole line, and then we can see just the output of X. We can even draw a quick histogram of X, and if we would like, we can say drop a histogram not a spelling course, of X. Great. Those are just a couple of examples of commenting code, and I realize that they might be trivial at this point, but trust me when I say that when your code gets to be hundreds of lines long, you will definitely thank yourself for commenting your own code, as well as any collaborators that see your scripts in the future and work on them. They'll also thank you for doing so. It's a real time save. Let's talk about some data types then, and also variable assignment. Take a look at line 6 again. This is something that I've sort of glanced over up until this point, but I want to explain a little bit more as to what's going on. What we're doing here is we're making the variable x, and we're assigning the value created by this function to x. Let's give another example of variable assignment. Let's say y. For one reason or another, I want the variable y to equal 5. So I'm going to follow sort of the same syntax or the same structure that I followed up here. X with a less than sign and a horizontal line. Looks kind of like an arrow pointing towards y. And we'll just give the value 5. If I run this line, you should see in this top right that the value of y has appeared, and we can see that it's 5. If I want to return that value of y, I can just hit y and hit Control Enter to run that line. And we see down here in my console that the value of y was returned. The value of 5, rather, which also happens to be the value of y, was returned. Now, R is just a fancy calculator, if you want to think about it like that. So you can also perform arithmetic, like y plus 5, or y divided by 5, etc., etc. The multiplication sign is not an X, it is an asterisk. So y times 5, for example, would yield 25. Now I want to show just one thing with this. I'm actually going to show what type of variable we're working with when we're working with y. And I can do that by using a function that's called type of. And in representing this function, I also just want to talk about functions in general. So the name of the function is called type of. And then notice, like in our rnorm or in our histogram, we gave the name of the function followed by an open and closed parenthesis with, in both of these examples, a value that was introduced into those parentheses. The name of the function is here, and then anything that's put into the function is called a parameter of the function. So, for example, I could change the parameter of my rnorm function to return 300 values instead, and that would change just slightly the output x that we get. The same here. If I want to know the type of the variable y, I can just introduce y as a parameter of my function type of. I want you to really get used to the language that I'm using here as well, because it's language that we'll use for all functions as we're working in R. So if we put y as a parameter of the function type of, we actually get the information returned as double. Now, double is a special type of numeric data type that is just a fancy word for saying this specific data type can hold integer values as well as decimal numbers up to a certain precision, and they're very precise numbers, doubles are. So another example of a double might be type of 100.51. Again, you see we've returned double there. So just remember, a double is a numeric data type that can be either an integer or a decimal number. The majority of numbers that you'll work in R are going to be doubles. There are certain reasons why you would try and make a double an integer number instead of a double, but for 99% of our use cases, we're fine just leaving it as a double. Let's contrast that with something like, let's name another variable. Let's say name. And I'll assign the variable name, my own name, Trevor. And you might want to check the type of the variable name. So again, the name of the function followed by parentheses. And then we're introducing the parameter name into my function so that it returns back the type of that variable. Let's run line 20, and you can see it returns character. Character is another data type that is very different from double. Remember, double is just a number. It can be an integer or a decimal value with a certain precision. Here, my variable name is being called a character. In a lot of other programming languages, they refer to this as a string. So it's just a string of characters that's anything from lowercase a to lowercase z, uppercase a, uppercase z, etc., and including any numbers from 0 to 9. If you bound that in our quotes here, the computer will understand that you're trying to express that that is a character data type. Let's give another little bit weird example. Let's say my number, my favorite number, and everyone's favorite number, of course, is 777, right? That's what you would like to see at Las Vegas. But let's put this number in our single quotes, as we did my name before. So my question for you is, how is the computer going to understand 777? Can I do math on my favorite number? Let's just say +1. I cannot do math on my favorite number. Oh, it's saying my favorite number not found. Let's go ahead and run this. And then we can see that we cannot do math on my favorite number. The error that I get is that a non-numeric argument was given. You might ask yourself then, well, what type of number is 777 then if it's not being considered as a numeric data type? Let's just check type of. And again, we're going to feed this function the parameter, my favorite number. And we see returned is character. So anytime you have quotes around a number, the computer thinks that you're saying that that is a character string that cannot have arithmetic performed on it, for example. And so this is more than anything a caution to you as a new user of R to just ensure that the data types that you're working with are in fact the data types that you need. For example, you can't perform any arithmetic on a string data type or a character data type in R, but you can on a numeric data type. The same goes for other functions in R. Say you want to capitalize a character so that all letters in my name are all capitals. You could do that on a character data type, but you cannot do that on a numeric data type. Those are just a couple of simple examples for now. In the future, if you run into this sort of error, non-numeric argument, or not a character argument, or something along those lines, you know that maybe the data types that you're working with are not the correct ones. There's one more type of data that I would really like to talk about because it's going to be important here very quickly, and that is the logical data type. So let's go ahead and create a logical variable, and we'll call it my logical variable. Now with a logical data type, you really have two options here. It's either true or it's false. So I can say my logical variable is true. Notice here that the text was highlighted a different color as opposed to such as a character is highlighted in green on my with my settings in R, and in yellow we have the logical data type highlighted. Notice also that I used all caps here. So if I go ahead and assign true to my logical variable, just running this line, Control Enter, I can see here at the top right that my logical variable ends up being true. What is the type of my logical variable? You could probably assume that that is a logical data type. Let me show you some shorthand with a logical variable too that you may or may not see in the wild, but let's give another logical variable. Failed to mention as well, you can name these variables whatever you would like, but just as with commenting code, both you and your coworkers will probably thank you in the future if you give these variable names a meaningful name that helps you make sense of what the code is doing in the future. So another logical variable, the shorthand that I would like to show you is, our other option is false, of course, but we can just give it a capital F, and R understands that the capital F stands for false. So another logical variable in my values is considered false. Let's just double check. Type of another logical variable, and we have logical returned. There's one more thing that I failed to mention up to this point that I would like to mention because it's a big time save. If you noticed, I was just typing out another logical variable, and RStudio said, whoa, this might be what you're talking about. You don't have any other variables that are named another something or other. And this is the only option that we found that kind of matches what you're trying to type out. If that's the correct option, go ahead and hit Tab, and that will autocomplete the variable name for you. You'll find that the tab autocomplete is very useful. It saves you time, and it also saves you from those ever-present spelling errors that you're bound to have happen as you're writing code. We get the logical data type there. All right, so all of this above is stuff about data types. Let's go ahead and just say data types. Just for posterity's sake, I have a fully documented, fully commented version of this as well. I just want to remind you that always commenting your code is very important. So let's go ahead and get into what a vector is. A vector is an object in R that holds a series of elements. The important thing about a vector is that every element in that series has to be the same data type. Let's give an example. If I want to make my vector, I can assign this variable named my vector a quantity in just the same way I do any other variable. So again, that's with the less than sign and the horizontal line, or the dash. Now, if I want to give a list of elements to this vector, I actually have to use another function in R that is just C. Remember, all functions in R are followed by open and close parentheses with our arguments or our parameters inside the parentheses. C is a function. C stands for combine in R. Some people think it stands for concatenate, which also makes good sense. C allows us to give a list of elements, and it will combine them together for us and create the output vector, which we'll see in just a moment. Let's give a really simple example. Say a vector of 1, 2, and 3 as numeric data types. So we can just give it 1, and I separate each item in this list by a comma, 2, and 3. If we run this line 32 with Control Enter, you can see that my vector appeared here in my values, and it's a numerical data type, and I have the values 1, 2, and 3. We'll get into what these square brackets mean in just a moment, but for now, we can see our values 1, 2, and 3. So, just to double check, let's go ahead and call my vector. Control Enter, and just see what it returns. Values of 1, 2, and 3. If we say type of my vector, my underscore vector, we get returned that this is a double, or remember, a numeric data type. The double is the special numeric data type that is most frequently used. Let's try something a little bit different now. Remember I said before that all vectors have to have the same data in them. Let's go ahead and put my name here and just see what happens. So my original intention might have been to have the numbers 1, 2, and 3 as numeric data types, and then my name as a string or a character data type. Go ahead and run line 32. We can see here that my vector has changed up in my values box. And let's take a look down here. What do you notice that's different about my vector from previously and now? Of course, we have the value of Trevor appended on there, my name. But look at 1, 2, and 3. They're surrounded now by our double quotes. And remember up here, we decided that double quotes, or quotes at all surrounding a number, indicate that that's a character as opposed to a numeric data type. Let's just double check that this is in fact a character. So all of the data held within my vector is now treated as a character. Say, for example, I wanted to perform some arithmetic on my vector. Say, every number in my vector plus 5. I'm going to get an error here because, again, it's treating this 1, 2, 3, and my name, Trevor, as character data types, and we can't perform arithmetic on characters. Go ahead and get rid of my name and reassign my vector with Control Enter. Take a look. We're back to a numeric or a double data type, and we can now perform arithmetic on my vector. In just the same way, we could divide everything by 10. This is another example of arithmetic performed on a vector. It's going to take in that whole list of objects and do the arithmetic on every element of that list, returning the value at each point. That's great. Vectors are very useful, especially if we want to apply math to several different things, but you do have to be careful that you're using the right data types. And remember that every object that's held within a vector has to be of the same data type. That's an important caveat. Let's give one more example. Well, we'll give a couple more examples of vectors. Say, for example, that for one reason or another, I need a vector full of the months of the year. Let's call this vector months and assign it, of course. Now, just as we did before, we need to use the function C for combine, open and close parentheses. And the argument that I'm going to give this function is just the list of months of the year. Say January, February, March, and so on and so forth. This isn't meant to be a typing exercise, but as you can see, if I run this months, and then I take a look as to what it contains, we have January, February, March. And if I look at the type of months, what do you expect the type of this vector is going to be? Of course, it's a character data type, right? All of those are surrounded in quotes, and they all look like characters in the sense that they're all just strings of letters, words as we understand them. The computer doesn't understand what that is, but we do. Let's say that for one reason or another, you wanted to find the first month of the year. Let me go ahead and finish this months vector out. All right, like I said, it's not a typing exercise necessarily for you guys, but I went ahead and finished off that months vector. Just to double check, our type is still character. Let's say that for one reason or another, you wanted to have the 1st, 4th, 7th, and 10th months of the year. That might be your quarters in a company that you work for, or for whatever reason you need those months. We can actually grab those months out of the months vector by using what's called indexing. Let's give a really simple example first. Say I want to know the first month of the year. That's pretty easy for us to answer. But in order to index that, or in other words, grab that item from the vector months, we go ahead and call the vector months. And we're going to use these square brackets that I kind of referred to earlier. These square brackets let you input a number for the specific index or the specific location that you're trying to get back from that vector. January is found in the first position of this vector. So if we wanted to return the first month and expect it to be January, we'll just give it a 1. If I wanted the current month, which is June, we can figure out that this is position 1, 2, 3, 4, 5, and 6 would be June. So I can ask for the 6th month in my months vector, and I should see the computer return June for me. That's interesting, but let's go back to our original question, right? We wanted the 1st, 4th, 7th, and 10th months of the year. Let's go ahead and do months. I could, of course, do each one of them individually. 1 and then another line with 3, or 4, and then 7 and then 10, etc. Or I can do something a little bit tricky and actually, for the indexing, feed a vector into the indexing and get those values from the vector back. So I wanted the first month, 1, 4, 7, and the 10th month. And you can see that I'm using my combine function here. And we'll return just those months that I was most interested in for whatever reason. So these are just a couple of examples of some relatively simple indexing. You may or may not find a lot of use cases for these depending on what you use R for. But I do want to show you a different type of indexing that is ubiquitously used no matter what you're doing in R. You need to know about this type of indexing. In order to show you this indexing, we'll call it conditional indexing. We are going to give you, we're going to instantiate, or we're going to create a new vector. Let's make a vector with the numbers 1 through 100. Let's call this numbers. And again, we're just assigning this. Use the combine or the C function. Now I could sit here and write out 1, 2, 3, all the way up to 100. Or there's a shorthand way actually for creating numeric vectors. I give it the first number that I'd like to start with, followed by a colon, and then I give it the number that I would like to end on. Now, if I Control Enter on this line and then run numbers with an S, I should see that we've counted by 1 all the way up to 100, starting at the value 1. If for whatever reason, I'll just show you another shorthand way of creating a vector. For whatever reason, let's say that instead of counting by 1, you wanted to skip count by 3. Let's just give that as an example. We'll call this vector skip count. And in just the same way, give it a C, open and close parenthesis. And actually, I'm getting a little ahead of myself. The function that we use is actually called seek for sequence, so a sequence of numbers. I'm going to give it the number that I'd like to start on, say 0. And let's say for this example, I want to end on 99. If I'm skip counting by 3, I'll give the example by, or the parameter by equals 3. And let's just take a look as to what skip count looks like. We've skip counted from 0 to 99, counting by intervals of 3 in each time. Great. Let's go back to our conditional indexing example here with numbers. So again, we have this vector full of numbers 1 through 100. Let's say that for one reason or another, I want to get from this vector every number that's evenly divisible by 5. What does evenly divisible mean again? It's just that when I do the division, I end up with an integer number as the result. For example, 5 divided by 5 is 1, and 1 is an integer, so that's one of the values I would be interested in. 10 divided by 5 is 2. Again, that's an integer, that's a value I would be interested in. 35 divided by 5 is 7. That's an integer. I'm interested in 35. A counterexample to that might be 53, for example. 53 divided by 5 is going to be 10 and a little bit, specifically 10.6. That is not an integer number, and so it's not a number that I'm specifically interested in. The way that I do this type of division is actually what's called the modulus. Let's give you an example. Say 7 modulus, and the sign for modulus is 2% signs. 7 modulus 5 means 7 divided by 5, return to me only the remainder. So think back to probably 4th grade when your teacher wasn't prepared to teach you about a fraction or a decimal yet. So they said, well, think of this as a remainder, where you can take 5 out of 7 and there's 2 remaining. Let's make sure that this math is working as we expect it to. So the modulus, after I take 5 away from 7, is 2. In our other example for 53, I believe was our number, modulus 5, we can take 5 out of 50 10 times, and then we have a remainder of 3. Is that right? There it is. So how is this going to help us learn conditional indexing? Back to our numbers. We wanted to get every number in numbers that was evenly divisible by 5. Meaning that if we did the modulus division of that number, we would get a remainder of 0, right? Because that's the only way to avoid a decimal or a fraction after all is said and done with the division. So in order to get anything whose modulus is equal to 0, we can use our logical function as well. Let's give an example with just this 7 modulus 5. Say we wanted to test 7 modulus 5 to see if it's equal to 0. When we're testing to see if something's equal to a value, we use double equal signs in R. Let's run this code. It says false. And that should be pretty intuitive at this point. What about 45 modulus 5? Is that equal to 0? And we return the value of true. So what we need to do is essentially apply this idea of a number in numbers, modulus 5, and ask the computer if that's equal to 0. So for every number in numbers, that number modulus 5, we're asking the computer, is that equal to 0? Does it have no remainder when it's divided by 5? And take a look at the output that we get. We get in the first position or the first index, false, 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 until the 5th index, true. Again, the 10th index, and then the 15th, 20th, 25th, etc. index. Those indices correspond back to the same indices in numbers that we originally started with. Remember, now the number itself 5 is found also in the index 5. And here, in our logical, the logical output from our logical function, index number 5 is listed as true. Now, if I wanted to index based on this logical output, I can just call the vector numbers, and I can index with the open square parentheses and the closed square parentheses. And this is going to go through every value in this vector, whose output is shown here, and it's only going to return those values in numbers whose value is true. Let's take a look. So we've only returned what ends up being 20 values here. 5, of course. 5 modulus 5 is 0. There's no remainder after that division. 10 modulus 5 is 0, etc., throughout our entire vector there. Conditional indexing, now with this example of conditional indexing, it might be a little bit trivial from first glance, because could we not have just skipped counted by 5 to get that same output? And that is true. But we wouldn't have had an easy to approach method of explaining conditional indexing. So conditional indexing will be used heavily in subsequent discussions in this lecture series, and it's something that beginners in R kind of have a struggle understanding. So again, let's walk through what we're doing here. If we wanted to index numbers, we just say numbers and give the open and closed square brackets. Again, we can give just a single number in numbers, or a single index. We can feed that to the numbers vector and get the value that's at that given index. I can also index based on a vector, such as 1, 2, 3, and that will return indices 1, 2, and 3, which also happen to have the values 1, 2, and 3. And I can even use a little bit more complex vector defined by this logical statement here, where every number in numbers undergoes a modulus 5, and we're asking, is that equal to 0? If we plug that in, then we get the statement that's on line 48, and the output that is any number that is evenly divided by 5. Alrighty, if conditional indexing is still a little bit fuzzy for you, that's perfectly understandable. Go through the examples that I've given in the accompanying notebook to this lecture and test yourself to see if you can conditionally index other things, say things that are evenly divided by 3 or 9 or whatever number you choose. You can even change the size of the original vector that you index, etc. Let's then discuss what are matrices, moving on from vectors. Matrices, as they're represented in R, are essentially just vectors of vectors, or a vector of vectors. Let's take a look at what I mean by that. Let's give a couple new vectors. We'll just say vector 1. Combine the numbers 1, 2, and 3. Vector 2. We'll combine the numbers 4, 5, and 6. And vector 3, following our same pattern, we'll combine 7, 8, and 9. So our vectors, our computer already has values for those variables up here in the environment. So let's see what I meant by a matrix is a vector of vectors. So we can use a function called cbind, and for the arguments or the inputs to the function, we're just going to give a series of vectors. So vector 1, vector 2, and vector 3. Let's check the output of cbind. We have vector 1, and its values are shown in a column. The next column over, vector 2, again, straight up and down in a column, and vector 3. cbind stands for column-wise bind. So these vectors have been bound together in a column-wise fashion. If I wanted to make something that looked more like the keypad on your telephone, you might use the function rbind for these given specific vectors. The inputs to this function are just the same as cbind. But you can see now we have the correct orientation. And if you look, we have vector 1, and it's laid out in this row-wise fashion, followed by vector 2 and vector 3. So this vector of vectors, or the matrix, is just like any other vector. All of the vectors have to be of the same data type. Let's give another example of that. So again, the way that we ruined the vector before was by giving my name. So we have what I might intend to be a numeric data type, and then we have character data type. Let's see how cbind appends those together, again in the column-wise fashion, but we can see now that the type of the data that's held in this vector is now all character. It's not flexible enough to let there be a couple of numbers and then a character string. It has to be all of the same data type, much like the regular vector is. So we'll go ahead and put this back to a 3 and just double check that that works again. Now I will say here that if you're into a lot of matrix addition, multiplication, linear algebra type use cases for R, there are a myriad of functions that are very useful for working with matrices. For the rest of us who don't work with matrices as often, I'm going to leave it at that. So if you're really into using matrix math for your work, go ahead and look up how to work with matrices in R, and you'll get a lot more detail. For now, I want to jump into what is probably the most often used data structure, and that's what's called a data frame. So the data frame is really the meat and potatoes of R. The reason so many people use R for statistical analyses is because data frames are just so great to work with. If you want to think of the data frame as kind of a glorified Excel spreadsheet, you probably wouldn't necessarily be wrong in that, but R just gives you so many more tools and is so much faster to work with that R is really the best way to be working with this sort of data. With that being said, data frames, unlike the vectors and the matrices that I kind of built on the fly for examples, it's not really practical for me to build a full data frame. It's like invent a whole Excel spreadsheet within R. It's not really practical. Instead, what I'm going to have you do is actually import some real-world data from a scientist called Phillips et al., and that data set is based on a bunch of sea turtle observations. So that data set is actually found on the page where you find the notes for this video lecture, the textual version of the lecture. Go to that page, download the Phillips et al. alldata.csv file, and then what you need to do with that data file is move it from your downloads folder into the same folder on your computer that you have your R project in. So remember, back from the first lecture, we created probably a new folder for you on your computer that was named R course or something similar. Move that data that you download into that same folder. I'll be here whenever you're done with that. Alrighty, so just to double check, at this point, you should have downloaded the Phillips et al. Alldata.csv and then moved it from your downloads into the same folder that you have the R project in. In order to read that data into R to actually work with it and show you guys what a data frame is, we need to use a function, of course. We're going to go ahead and call the variable data frame, df, common abbreviation. And we're going to use the function read.csv. So just a little aside as to what a CSV file is. It stands for comma separated values. So essentially, in the data frame, we have rows and columns of data. Every row of data, or every observation, if you want to think about it with that sort of lingo, every row is its own row in the CSV file. And then a single row separates its columns with a comma. So let's go ahead and read that comma separated values file in. And we need to give it, you can see the kind of text bubble here popped up and said, we need to feed it the file name. So we do that. It's expecting a character data type. So we'll give it a couple of quotes. And as long as it's in the same folder that our project is in, you should be able to find it using Phillips. And if you autocomplete, Phillips with 2 L's, I guess, if you autocomplete, you can get the entire name of the data set. Go ahead and hit Control Enter. At this point, if you're having problems reading in the data set, it's probably because it's not in the right directory. And I'm sorry that I've reiterated that so much. It's just a very common point where students have trouble, is the file is actually not in the same folder that they think it should be in. So if you're having problems or errors, pause the video and make sure that you have that in the right place on your computer. Now, in order to visualize this data frame, we can view and then data frame. View with a capital V, by the way, which is a little bit weird. And this is what the data frame looks like. So it's 3 columns full of 13,256 observations, according to this. So we have 13,000 different turtles, presumably, or maybe the same turtle measured on a different year. Different measurements for those turtles based on when they were discovered. We're working with 2 species in this data set, Caretta caretta and Chelonia mitis, I think. It's the other species. We'll find that in just a moment. But just stop and contemplate for just a second. What do you think the data type is for the species column? It looks like text data, so it's probably a character, right? What about for SCL? SCL, I can't remember right now off the top of my head, but it's something to do with the length of the shell. We'll detail that more in another lecture. But what type of data do you think is contained in SCL? Numeric. You could specify even more than a numeric data type. You could say it's probably a double. What about the type of data that's housed in year? You might think to yourself, oh, well, year is a number, right? 1982. It's probably a numeric data type. I would actually argue and say that year is probably better considered as a character data type, even if the computer thinks that it's an integer value or whatever. It's probably best considered as a character because you don't really do arithmetic with years, right? Especially in a data set like this, you don't really want to be manipulating that. So it's probably a character as it's recognized. Now, another handy function to look at the data frame, aside from view, is actually head. And we'll give it the data frame, of course. The output here is the first 6 observations, this first 6 rows with, of course, every variable that was observed. So the species name, the SCL, and the year of that observation. So head is much the same as the same head in the Unix-based operating system's command line. So if you use the head command in a command line, it's the same spirit here, essentially. The head of the data frame is just the first couple lines. Another function that's useful is str, which stands for structure. we'll go ahead and give it the data frame. Again, it's telling us how many observations of how many variables, but it also gives us a little bit more detail into what the variables are. So the variable names were, again, year, SCL, and species. And we can see that the data type, so RStudio is actually recognizing this as an integer, which, like I said, we probably wouldn't do math on that, so probably consider it as a character better, but I digress. SCL is being considered as a numeric data type, probably a double. And then species, remember we said species is probably a character, but this is telling me factor. So I think it's worth talking about what a factor is really quick. And we'll do so by working with the specific species sort of column, the entire column. If I wanted to grab just one column of the data frame, I actually use a $sign. You can see here that these are the columns that are available to grab, and I wanted to work with species. So df $, species. Now this is saying a factor with 2 levels, carita, and then it's not telling us the other level. If I wanted to know the other level, I could use the function level, or levels, and these will tell me the 2 levels of this specific, what ends up being a vector, because it's a column within my data frame. All columns of the data frame are vectors. They have the same data type. So we end up with carita, forgive me if I'm pronouncing these wrong, and Chelonia Midas. So the factor data type is just saying that essentially you have a small group of options where it's either carita in this example, or it's Chelonia Midas. It's not anything else. So it's not a full-on wide open character where it could be anything as long as it's a character. It's a character that has to be either of the 2 options that are provided for us. There are, of course, other examples with more options, but just an example for you. Now, a couple other functions are the dimensions of the data frame, for example. We already kind of know this from up here, but we have 13,000 observations with 3 variables. And we'll just give you one more function for working with data frames, and that is actually names. I'll just show you the output, and the output is just the names of the columns or of the different variables that you're working with, if you want to think about it as variables. Columns are variables, and then rows are observations. So that is really all I would like to talk about data frames. But I hope that more than anything, you guys understand that every column in a data frame is essentially a vector. So all the stuff that you can do with vectors, you can also do with an individual column of a data frame. So if you think of stuff like conditional indexing, traditional indexing, etc., you can do all the same things to a data frame and the individual columns of that data frame. Of course, this is really just the very surface of R. We're about to get into the most interesting stuff, which is actually doing analyses based on these data frames. But for now, this second lecture, that is all the content that I wanted to cover. So hopefully up to this point, you've understood the basics of working with vectors, understood, at least conceptually, working with matrices, and if you're using a lot of matrices, that you have some resources to work with those with. And for the data frames, of course, being sort of the big idea that I wanted to get to. And we will, in the next lecture, work through how to work with these data frames even more. And we will also do some summary statistics, some plotting, and really exciting stuff. We've really just got the surface of R, and we're really ready to start going on the very interesting, very fun stuff to do with R. So, thank you for watching.